calculate limiting reagents, you're going to identify this type of problem by seeing two quantities of reactants given with one substance likely being used before the other. For example, when you're burning gasoline, the gasoline usually runs out before the amount of oxygen is depleted. So basically this is going to be the same type of stoichiometry we've done before, but this time you have to calculate the amount of moles from both. And the smaller amount is going to come from the limiting reagent. Okay. So we're going to complete an amounts table. I know the book introduced this to you in one of the summer assignments, but a lot of you had difficulty with this, so we're going to take a look at doing that again. Right, we need to start by writing the balanced equation. So when you see the iron 3 bromide and the sodium sulfide, you should basically be able to recognize this as a double replacement reaction. So I'm going to stop and write the equation. And next we need to balance the equation. This is a pretty basic one. If you always start with the most complicated formula, you'll erase less often. Okay, and then we need to know what the precipitate is. So we need to know something about solubility rules. And AP requires you to know that any of the alkali metals are aqueous, so that automatically tells you that this is your solid. And next we want to fill in what we know. So we initially have 3.5 grams of this, 6.4 grams of this, and we'd have nothing of either product. So to calculate precipitate, we need to do two bridge problems, one for each of our substances. So one for the 3.5 grams of FeBr3 and one for the 6.4 grams of Na2S. In both cases, we're going to calculate for the moles of Fe2S3. So typically we'd probably go all the way to grams, but we don't have to do that step for both of them until we figure out which one is the limiting reagent. But I do have to do grams to moles for each. And then I need to do the mole ratio for each. So it's 1 to 2 for the FeBr3. So 1 mole of the Fe2S3 to 2 moles of FeBr3, and 1 mole of Fe2S3 for every 1 mole of Na2S. And I'm going to calculate at this point to compare the number of moles. So when I have these two mole values, you'll see that the moles from the FeBr3 are less than the moles from the Fe2S. So this tells us that this is our limiting. Notice I'm going up to the top to rate it, and this is our excess. So what that tells us is all of this is going to be used up. So after the reaction, there will be no more FeBr3. Now to calculate, we're going to continue from here. So I'm going to do this times its molar mass to get grams of Fe2O3. And once I multiply by the molar mass of the Fe2S3, that tells me that I get 1.2 grams of the Fe2S3. So this really does answer the question. We know what's limiting, and we know what mass of that. So we don't need to complete the whole table for this problem, but I'm going to show that to you on the next slide just so you see another example of this. So to complete the table, I'm going to start with the smallest number of moles that we just calculated, the 0.0059 moles of iron 3 sulfide. And I'm going to do two more calculations. I'm going to figure out how many grams of Na2S that requires, and I'm going to figure out how many grams of NaBr it's going to produce. So in both cases, I'm going to use mole ratios again and molar masses. So I need 1 mole, and to that same value, 1 mole to 3 moles of Na2S. And then the molar mass there of 78.06 grams in 1 mole, which gives me 1.4 grams of sodium sulfide. So that's going to be how much was used up. So that tells me we have 5 grams of that in excess left over at the end. And then for the NABR, it's a 6-to-1 mole ratio. And the molar mass of NABR is 102.89 grams to create 3.6 grams of product. Now again, we didn't need all of this for this problem, so the only things that we really need to know for this problem were what's the mass of precipitate formed, and we needed to know which was limiting, and in this case was those two values. We just wanted to see a complete table, amounts table. Okay, in this reaction, example number 2, you'll see we have aluminum bromide and chlorine, so we are going to write a single replacement equation with aluminum bromide reacting with chlorine. So the chlorine is going to replace the bromide to give you aluminum chloride and bromine. Okay, and then to balance that one, we need 3 and 3 and 2 and 2. Okay, if we write in our amounts, we have 25 grams of this and 12 grams of this. Okay, so again, you'll see our first question here is limiting reagent, so we needed to set up our 2 bridge problems, starting with each of our amounts of reactant to figure out how much is limiting. So if you look ahead, how many grams of compound, so we're going to calculate based on this just because it asks for the grams of So we need to convert each of our grams to moles, and then use the mole ratio to find out the moles of aluminum chloride in our problem. And you can either do the same step for each of your bridges like I'm doing, or you just complete one and then start the other. It doesn't matter. So mole ratio is next. And you may notice that this is a 2-to-2 ratio. You could reduce that down to 1-to-1, but I just always just take whatever's from the balanced equation. Either is acceptable as long as you account for the fact that they're the same. And then the 2-to-3 ratio for aluminum chloride to chlorine, and then you just are going to calculate your moles. So this time you may notice that the 0.0937 is your lowest number of moles. Notice it didn't come from the smallest amount of grams, so you can't just look at grams and take whichever is lowest. It worked out like that in the last problem, but that was just a fluke. You always need to look at mole ratios. So this one's going to be our limiting. So I'm going to put an LR and an XS over there, so for limiting reagent and excess reagent. Okay, and I also wrote in the amount here. Okay, and then I'm going to continue to do a bridge problem and figure out moles to grams to answer the second question, how many grams of compound would be produced. Okay, writing with the stylus is fairly difficult, so you're seeing I'm running out of room, but if you can do this on your paper, just keep running this out as one continuous line. And that is going to give you 12.5 grams of aluminum chloride. So again, if I'm adding that back to my table, and because this is limiting, we know that this is all going to be used up, so there would be none of that left at the end. So this time they're asking us to calculate the excess reagent. To calculate the amount of excess reagent, I'm going to start with the moles of aluminum chloride calculated. So I could start with this 12.5, but it just would require me to do another step. So I'm going to go back to my 937. 0.0937. And I'm going to calculate grams of Cl2. Ratio for aluminum chloride to chlorine. And then the grams of chlorine per mole, which is 70.9. I'm ready to calculate that, which gives me 9.97 grams. So that's how much is going to be used. So if I go back up to my amounts table, minus the 9.97 grams, which will give me a total of 2.0 to sig fig. next example follows a similar pattern. The only thing it adds is a percent concept in this. So you'll see that there's 80% pure copper, so that means you're not getting a whole 250 grams of pure copper, but it follows the exact same steps you're going to need to do the percent calculation before you do your grams. It would be a difficult equation for you to write at this point, but this is a redox reaction, so you're going to see changes in oxidation number. Anytime you see an element, that's typically something that tells you that you have a redox equation. So, sorry, my U is so bad. Okay. And then we're just going to balance this guy. And we'll explain where that comes from later. So the first part of this will start out very normally, where you're going to take, this time, 3 reactants with their initial amounts. We have 100 here, we have 50 here, and we have 250 here. So all of the initial amounts will start the same except for this one. So it's not really 250 grams, so I've got to do 80% of 250 grams first to get my amount of copper. So this is going to be 200 grams of copper instead of the regular, but in all cases, it doesn't really tell you which one to calculate, so I would just do the one that's easiest since it doesn't specify, or if you look ahead, you want to know methane, so I'm going to calculate moles of CH4 for each of these. Okay, and I'm just going to work through these, so you're going to see these flash on the screen, so you might want to pause if you want to catch up. I'm not going to complete the amounts equation for this one, but you're going to see that the limiting reagent is going to be your smallest one. So copper, even though it's the biggest amount, is the limiting, and it just says how much methane. So I am just going to chop this one off here because you have a very long video here. So I have some practice problems there to work on in the book. If you have any questions, please contact me.